of course, right? Okay. All right. And so what we're going to be doing is we're going to be talking about gases. So, what do you, if anything, what do you remember about the kinetic theory of matter from middle school? Does anybody remember anything? So, what does anybody remember from the kinetic theory of matter? Lily. Excellent. Gases have the most kinetic energy of all the states of matter. Does anybody know what kinetic energy is? Yeah. Kaylin. Reagan. Yeah, it's the energy that we have from movement. Right. It's the energy we have from movement. Great. So the energy of movement. So in fact, what you learned is, which you may remember, is that particles of solid are all lined up and they're just sitting there like vibrating, but they're all next to each other. And then what you learned is that the liquids are moving a little bit faster and they're moving around a little bit more, right? And that then you learned that gases are like pew, 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 all shooting all over the place, right? But what you didn't learn about, which we are going to learn about this year, is that the reason is for that is because of intermolecular forces, and we're going to talk about that. Those are forces that are between the molecules, And that solids, because they're all lined up like that, they have the strongest intermolecular forces, and gases, because they're going pew, 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 pew. Actually, they have no intermolecular forces at all. They have no attraction to any other particles. And that's why they shoot all over the place and do whatever they want. So the kinetic theory of matter, gases have the highest energy and they have the lowest. They have the highest energy and the highest movement and the highest volume, and that. So we're going to do all of that in this chapter, comparing all of those things. But first, what we want to do is we want to talk about what the kinetic theory of matter is. It describes the behavior of matter in terms of three things, and we're going to look at those three things in terms of one, the size of the particles compared to the space that they're in. As in the volume that they take up. So remember, in a solid, those particles are all tightly right up next to each other. So the volume that that solid takes up is exactly the same basic volume that the particles take up. Whereas in a gas, the particles are shooting all over the place, so there's a lot of space between those particles, which means that the volume that that object, which is gas, takes up, is a lot of it is space. How much of it? A huge amount. A very small, very, very, as my mother would say, very, 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 she said three very woman, very, very, very small amount of space is taken up by particles. All right? Very small amount. Very, very, very small. So small that we think that a balloon is inflated because it's filled with these particles. So it's all full of particles. But in fact, that isn't even true. A balloon is full because the particles inside are banging against the wall of the balloon. That actually is why the balloon expands, because the particles of helium are banging against the, pew, 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 banging against the walls of the balloon. And there's so many of them that they keep the balloon expanded. And actually, if you listen to a balloon, you can actually hear the particles banging on the walls. You don't hear them individually. What you hear is a constant sound inside the balloon. And that sound is particle movement inside the balloon, because balloons are very loud, as you know. They're not quiet objects. And so what you hear inside that taut latex is the movement of all the particles inside the balloon. Okay, so very small. Number 2, the motion of the particles. So in this case, the motion of the particles is like pool balls. So it is constant, random, and in a straight line. They collide with each other. The balls, the molecules do like the pool balls. They collide with each other. And kinetic energy is transferred to the other particle. Okay. So what happens is, just like in pool, the pool ball comes up, it hits another pool ball, the first ball stops and the second ball starts moving because the energy is transferred. And number 3, the third property that kinetic theory of matter looks at is the particle's energy. This is determined by the particle's mass and velocity. We have a formula for this because it is kinetic energy. And so we use the same formula that physics uses. Kinetic energy is equal to 1/2 the mass times the velocity of the particle. So this shows you that the only things that are involved in the kinetic energy of a particle is the mass of the particle and the speed at which it's going. So m equals mass, and the v is equal to velocity. All right, so let's start talking about some actual properties of gases. The first one we're going to talk about is temperature. Temperature is defined as the average kinetic energy. So the average energy of movement, bless you, of particles in a substance. So the average movement of all the particles in a substance sums up to the temperature of that substance. So it's not like, well, they just happen to be the same. No, they are, that is what the temperature is. So in other words, the units Kelvin, Celsius, and Fahrenheit are actually units of kinetic energy. As the kinetic energy increases, so does the temperature. That's what the definition of temperature is. It's the average kinetic energy, okay? So as kinetic energy increases, temperature increases. They are the same. So therefore, temperature is dependent upon mass and velocity also. Is that Gray sleeping? Oh, okay. Yeah.
This might be a stupid question, but does temperature have a weight?
No. It's energy. So I mean, I guess you could say that maybe Einstein would argue that. I don't know that. Okay. Next. Particles as gases. So that's what we're going to talk about next, is specifically particles that are gases. So first, they have a low density. And this is because they have fewer particles per volume. Per volume. And they can be compressed. And now the reason that they can be compressed is because they have so much space. I mean, so much space. It's not even like, hey, they have a lot of space between the particles. They have so much space between the particles. It's like the Earth and the stratosphere space between the particles. They have a huge amount of space between the particles. And so when you try and push these particles together to compress the volume of a gas, you can easily do it because those particles have a huge amount of space between them. So they can be compressed and they can expand. Well, why can they expand? They can expand because if there's more room for them to go pew, 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 they're going to do that. They're going to do that until they hit the walls. That is what gases do. So they can be compressed and they can expand. So if we were to have one of those plunge things that that Wile E. Coyote had, right, in the Roadrunner, and it was filled with gas at the bottom, and so he pushed it down, and when he did that, this volume inside the plunger dropped because he was pushing down the plunger to decrease that volume. He could compress that gas very easily. So this is like a syringe. The gas inside the syringe can be compressed very easily. If the plunger was lifted up, that gas, those particles in there, would fill that plunger, the space, the volume would increase also. This is very important in terms of calculations of gases, as you're going to find in the next chapter, which is my favorite chapter of the entire year. So the gases will fill up, right? Okay, so gases move in two different ways when they're moving around in here. So the first way that the gases can move is through diffusion. Does anybody remember what diffusion is from last year? No, it is dispersing, but it's a very specific dispersal. Yeah? It is a little like tea. It is a little like tea. Landry? It's what? So it's through one gas into another gas, but what it is from a high concentration to a low concentration. All right? So in other words, this is why we can smell those dirty diapers in the corner even though we're all the way across the room. Because high concentration where the poopy diapers are, low concentration where we're standing, right, all the way across the room, but we can still smell them. Why is that? Well, the gas is moving from a high concentration through other gases, diffusing through other gases, over to where I am. No poopy smell over here. Oh, here comes poopy smell. Well, poopy smell is actually poopy particles that are small enough that they can float on the air, and then they get in your nose and you smell poop because, now there's poopy particles in your nose. So it sort of gives you a whole new appreciation for masks, doesn't it? I think it does. Right? Because yes, it's true, it's not going to catch all of them, but it's sure going to catch some of those poopy particles in it. All right. So from a high concentration to a low concentration, just like diffusion in biology. High concentration to a low concentration in biology, it's across a semi-permeable membrane. In chemistry, it's passing through other gases. All right? The other way that we can move here for gases is something called effusion. Effusion is movement of a gas through a pore. So an example of this is helium moving through the pores, through pores on a balloon. That's an example. When the latex balloon is stretched, the pores are large enough that the helium particles can get through, right? But as it deflates, the pores actually get smaller, and eventually they get to a point where the helium can't get through, and that's when the balloon is like 6 inches off the ground and it just sits there for days going bloop, 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 because the helium can't get through anymore, and so it just stays in there. Till finally your cat gets to it. Pokes holes in it. All right? Questions on anything so far? Okay, now as we're doing calculations, there's a couple of things that you need to keep in mind. First, a rate is equal to something over time. Anything. So if I tell you that I can walk at 4 miles Okay, so the formula looks like this. The rate of A over the rate of B is equal to the square root of the molar mass of B over the molar mass of A. So this is the relationship. It is the inverse relationship with the square root. Notice I inversed my molar mass, all right? And then I took the square root. So let's look at an example of how this works out. At the same temperature, which is faster? O2 or N2? And how much faster? All right. So first, you can figure this out immediately, right? Without any calculation at all. Which one is faster, N2 or O2? How do you know? N2 is lighter. It's a smaller particle. It's 28.02 to 32. It's a lighter particle. It says right here, the rate of effusion increases as the mass or size decreases. The smaller the object, the faster it goes. Okay? So, great, N2 is smaller. Next, how much faster? Now we have to run some calculations. So this is the way this works. My recommendation is you put the smallest one on top. No matter, just like limiting and excess, it doesn't matter which one you put on top. It'll still work out fine. But if you put the smaller one on top, it comes up with the final answer that your brain gets better. You know what I mean? It understands better, but it'll work out either way. So here I go. Rate of N2 over the rate of O2 is equal to, and now I'm going to flip them. The molar mass of O2 over the molar mass of N2. Okay, equals the square root of 32, which is the molar mass of O2, over the molar mass of N2, 28.02, which is equal to 1.069. So the big question is, that's great. Doing that math is simple. Got it, no problem. But what does the math mean? What did you just find? If I said, so what does that mean? You'd say, I don't know what that means. I don't know what I just found. So let's see, what did you just find? So what you just found is that the rate of N2 over the rate of O2 is equal to 1.069. Yes, I know that, over 1. Oh, wait, we're starting to get somewhere now. So now, because they're rates, just for the fun of it, let's throw in some rate units and see if we get it even better, okay? Meters per second. So now what I'm seeing is, if my N2 is traveling at 1.069 meters per second, how fast is my O2 traveling? 1 meter per second. That's what I just discovered. That's what my 1.069 means. If my rate of O2 is 1 meter per second, my rate of N2 is 1.069. Which one is now going faster? N2, because now meters per second is an actual rate, and I can tell. Not only that, but I know that if the O2 is going 2 meters per second, the N2 is going 2.138 meters per second, which is twice 1.069 because this is a ratio. So if I'm going to multiply the rate of O2 by 5, because it's going 5 meters per second, I'm going to multiply this one by 5 too, and that's going to tell me how fast the O2 is going. Are you starting to get the drift of this? The bottom line is the N2 is going 1.069 times as fast as the O2. Is everybody seeing this? The reason I know this is because I got 1.069 and N2 is on top. See that? So when I lay this out, I can see N2 is 1.069 and O2 is 1. Okay? Got it? So that means my final sentence here, in answer of how much faster, N2 is 1.069 times as fast as O2. Got it? Let's do another one. Okay, here's another one. At room temperature, xenon has a speed of 240 meters per second. So I know that's a rate. At the same temp, what is the speed of H2? So the first thing is, which one is lighter, H2 or xenon? H2, so that one's going to go on top. So the rate of H2 over the rate of xenon is equal to the square root of the molar mass of xenon, right, over the molar mass of H2, right? Which is equal to the square root of 131.29 over 2.02. So let's be clear about what I have now. The rate of H2 over 240 meters per second is equal to 8.06. That's what this comes out to. The square root of these two, right? Everybody with me? So now I'm going to put this over 1. And the reason I'm going to do this is because now I get to cross multiply and divide. And you know how much we all love cross multiplying and dividing. So when I do that, I get my rate of H2 is equal to 1.9 times 10 to the third meters per second. That's my answer. Questions? So I did the exact same thing. Yes, Maddox.
Where did that come from? The rate of H2?
Rate of what?
The rate of H2, like the 1.9?
I multiplied and divide. I said 1 times the rate of H2 and then 240 times 8.06. Right? Yeah?
So what would be the answer? Like how many times faster would it?
It didn't ask that.
Oh.
It's 8.06 times faster. See the 8.06 to 1? So this is like 8.06 to 1 is what to 240. So I cross multiplied Everybody understand? And I got 1 times rate of H2 is equal to 240 times 8.06. Okay? So look at question number 2. If you look at question number 2 on your worksheet, why is this question different? And you're doing the Graham's law side. Why is this question different?
You get time.
Is what? Thank you. Why is this question different?